Well, folks, to avoid any issues with this new headphone, just to give you some more details that you don't really need to know, I got a converter to go from this audio jack to C-type connection to my computer, and I tested the sound. It spooked me a little bit because the sound was going through, the PC has to know where to play it and so on. It seems to be working, so I'm going to record it this way, and we'll test again to make sure, of course. So this is a nice review again. Actually, I'll take two papers on this topic to talk about the contrasts, commonalities, and causes of the differences in Arctic and Antarctic sea ice change. There's been a lot of news about how the Arctic sea ice loss is very rapid and lots of discussions on those. Polar amplification is strikingly different at the two poles. Antarctic sea ice has a mixed trend at best, but more and more news about how it's also melting away recently and so on. So you have to always keep up because things are changing rapidly, and you have to make sure that the paper hasn't become outdated already in terms of the contrasts, right? So this paper doesn't have this trend, but I'll show it just to remind you that whether you look at the long-term trend from 1901 to 2023 for the land ocean temperatures, or just the recent period of 1994 to 2023, you can see that the amplification in the North Pole, polar amplification is very, very strong, whereas the southern pole is you know, very mixed because, of course, of the Southern Ocean, which complicates things by isolating the Antarctic. And as the ocean warms, the atmosphere warms, more snow can fall. So even the sea ice, vertical structures, atmospheric circulation, snowfall rates, regional contrasts over the Antarctic. Antarctica is a continent, whereas Arctic is ocean, very fresh, so freezes very differently, and so on and so forth. So all those things matter, but I'm again going to be fairly brief. Follow up on the paper if you do want more details. It's a very nice paper, of course, with lots of references. Uh, Keywords here, of course, sea ice, Arctic, Antarctic climate, and satellite. Arctic sea ice has declined precipitously in both extent and thickness over the past 4 decades. By contrast, Antarctic ice has shown little overall change, but this masks large regional variability. Climate models have not captured these changes. That's already a bad news, but these differences do not represent a paradox. The processes governing and impacts of natural variability and human-induced changes differ markedly at the poles because of the ways in which differences in geographical control and the properties of and interactions among the atmosphere, ice, and ocean. Arctic typically has very thick sea ice because it's a semi-enclosed sea, much fresher. Southern Ocean is wide open, and of course, Southern Ocean has much more. It's a channel, so it can take up much more wind energy. So the Ekman currents can go deep all the way to the bottom. Heating can go to the deep, can inundate the Pacific and the Indian Oceans. Indian Ocean has a fast connection because it's closed off to the north and so on and so forth. The impact of natural variability on ice cover is large at both poles, so modeled ice trends are not entirely inconsistent with the contributions from both natural variability and anthropogenic forcing. So even the response of the atmosphere-ocean systems and interactions at the two poles are different, remarkably different, because the North Pole has much more land. Jet stream is very strong, becoming wobbly because of all these land warming contrasts. You can see the contrast in land warming is not small either. So all these interact with the polar regions, and this, of course, being a channel, has a very different jet stream interaction and variability and so on and so forth. Okay, all those things matter. And I also noticed I say so on and so forth a lot. Maybe not a lot, but I say it often enough. Okay, so how the natural variability, which are already different in the two places, two poles, are going to respond to anthropogenic forcing itself is also complicated. So all those are also going to feedback to the natural variability response and anthropogenic variability. So polar amplification is ice albedo feedback, which we'll talk about a little bit. So despite this concurrence, the coupling of natural climate variability, climate feedbacks, and sea ice is not well understood, and significant biases remain in model representations of the ice cover and the processes that drive it. So we'll just get an introduction here with a few figures. I love figures which have a lot of messages, but I will skip a lot of the text, a lot of very nice, useful text with lots of details on the processes. The introduction, the area of the northern hemisphere covered by sea ice has declined dramatically since the 1990s. The decline is particularly evident in summer. That's critical because the September sea ice in the northern hemisphere determines how much more will freeze in the fall, winter, or it will just not uh, grow in extent or thickness. The summer minimum ice extent dropped to 40% below its long-term mean, an anomaly that was almost twice the previous record from 2005. This record was again surpassed in 2012. At the same time, global climate models did not capture the observed declines, even prior to 2007, which drove suggestions that Arctic sea ice might be nearing a tipping point beyond which irreversible changes in ice extent irreversible changes in ice extent changes would lead rapidly to an ice-free Arctic in the summer. This is, of course, we are always a little excited, and tipping points keep coming up in everywhere, but we have to be careful. Simple projections of trends suggested that an essentially ice-free Arctic could be imminent, but despite such concerns, Arctic summer ice cover has not declined further. But this is from 2015, so you have to be careful because we have had strong El Nino in 25, 2015, 16, and 23, 24. So we need to check these. These recent Arctic changes stood in stark contrast to those in the Antarctic, where the ice cover overall has increased modestly in extent over the past several decades and reached successive record high maximum extents from 2012 to 2014. Again, we need to look at later data which shows that there have been some dips in the very recent years after 2014. A contrast that has been called an Antarctic paradox in terms of the sea ice changes in Antarctic versus the Arctic, while the increase in is small relative to the decrease in the Arctic. DCMs again fail to accurately capture the observed behavior, instead suggesting that modest declines due to global warming should have begun. So models are, of course, struggling with a lot of things, but they are amazing because you give it the energy at the top of the atmosphere coming from the sun. They can do so many things: El Nino, La Nina, monsoon, Indian Ocean dipole, Atlantic Nino, North Atlantic oscillation, PDO, Arctic ice, Antarctic. You have to be careful because not many models do land ice. Sea ice is easier to do, and so on. So what is missing in the models in terms of the representation versus what is missing in terms of process representation, physical representation of, say, let's land ice or uh, sea ice thickness, all those things can matter. So quickly here, the geographic setting of Arctic and Antarctic sea ice. So you can see the Arctic Ocean here, Kara and Barents Sea is here, Greenland Sea is here in this color. So it's a semi-enclosed, fairly fresh because of all the snow melt and rivers that come in, as well as um, the sea ice that releases brine and has circulation from the Atlantic and out here in the Labrador Sea. So you have the Baffin Bay, Hudson Bay, Bering Strait, Bering Sea, and so on, and Sea of Okhotsk as well. So here in Antarctica, you have the Weddell Sea, which gets a lot of mention, Ross Sea, which is over here, Western Pacific Ocean, and the Indian Ocean sector here, and Amundsen seas here and Bellinghausen seas together with that here. So all these are geographically identified. Of course, Pacific and Indian Oceans are well known because they go into, uh, towards the equator and beyond. But Ross Sea, Weddell Sea are more regional seas that interact with the Southern Ocean the response here isn't. Okay, see you in a minute. Folks, as you saw, it got disrupted over suddenly, so I'm restarting just to go a few more minutes before we end this podcast. This will take a couple of podcasts, and then there's another paper. So we're talking about Arctic-Antarctic contrasts. I got cut off when I was just talking about the regional seas here, the Weddell Sea, Ross Sea. Uh, I need to go into the full mode first. I'm always kind of slow on these things. I was mentioning Weddell Sea, Ross Sea, Amundsen Sea, Bellinghausen Sea, which are regional seas trapped within the Southern Ocean is on the outer edge, and then they merge with the Pacific and Indian Oceans and Atlantic Ocean. SAM, Southern Annular Mode, similar to the Northern Annular Mode, Amundsen Sea Low. These are the acronyms used in the paper, which we will not come across, but I just want you to look at them to make sure that you are aware. uh, in general, I'm not always sure who the audience are, how much background you have in these things. So sometimes you have to assume that it's new audience that is looking for basic introduction, and the review papers in general have such acronyms listed as well, the important ones. Ice extent, the area of the ocean surface that contains sea ice exceeding some threshold fractional coverage, usually 15%. Global Climate Model, GCM, of course, you must have known. Multi-year ice that has survived through one or more summers. And when you look at trends, you're always trying to see how much of the old multi-year ice is disappearing, like 5-year ice, 4-year ice, 3-year ice. If everything is just new ice, then you expect that that's going to have a hard time growing because it has to survive the summer, and then fall and winter it can grow, etc. Deformation, the process of ice thickening through rafting and ridging as flows collide due to winds and currents. IceSat is the ice cloud and land elevation satellite from where a lot of data is obtained here. First year ice that has formed during the current winter season, and El Nino Southern Oscillation, of course, the famous interannual climate mode that I have many podcasts on. So this is a long title for the paper, sorry, the processes shown here. So in A, we are looking at the Arctic, and then in the second one, we look at the Antarctic. So this is these are the main processes. So increased intrusions of warm air, a lot of heat waves, as you know, lofty waves from the tropical regions are making all the way into the Arctic and also Antarctic. Lots, warm record temperatures. Antarctica has suddenly become green, which is really bad news because green means reduced albedo compared to ice and snow. So you can have a growing positive feedback. So increased intrusion of warm, moist air from both sides. So you can think of solar heating of the exposed ocean, the ice albedo feedback, increasing ice motion, absorption of solar radiation by melt ponds because of the ice albedo feedback again, reflection of radiation by snow and ice, which is the albedo effect. The lapse rates in the atmosphere are shifting, so declining multi-year ice, which means the thickness of the ice cannot be very uh, high, very large when you have first year ice, warming of the near surface atmosphere, either due to intrusions from outside or local changes in, let's say, ocean warming causing atmosphere warming, radiative warming by clouds and water vapor. So this is a complicated issue in the Arctic. People talk about ice albedo feedback, but there are also water vapor feedback. Polar amplification has to be explained. Plus, there is Atlanticization going on where Atlantic waters are coming more and more into the Arctic with very different properties. If you change stratification, you're going to change the ability to form ice positively or negatively depending on how changes happen. Solar heating, melting ice and stored in near surface waters beneath the surface mixed layer, increased Pacific flow, increased Atlantic flow, so Bering Strait connection there. Temperature and salinity profiles in the ocean, you can see how complicated it can get. Temperature can have, you expect a mixed layer, the fresh surface water layer, where vertical mixing turbulence is causing, or brine rejection is causing convective mixing and so on. And then you have complicated structures based on water intrusions. And you have cold halocline layer, temperature and salinity profiles in the upper ocean itself, warm Atlantic water coming in, increased thin ice growth driving deep convection and enhanced vertical mixing, which means you're going to bring more heat to the surface and lose it to the atmosphere. Ice is a very good insulator, and ice-free regions can lose orders of magnitude more heat compared to the region of ice-covered ocean, right? In the Antarctic, you have reduced solar heating of the ocean in spring due to increased ice cover. So you can see that's the Antarctic story there. Southern winds expanding ice cover and cooling the ocean. So you are spreading out the ocean, and there are changes in precipitation, which is a complicated story. As I said, if the ocean is warming, it can affect the shelf ice flowing glaciers onto the ocean from below and melt them, but warm ocean, warm atmosphere, moist atmosphere also can mean more snowfall in some places. So you have meltwater again affecting freshening of the surface water and trapping of heat at depth due to increased freshwater transport and strong winter ice growth. Of course, you have circumpolar deep water and more complicated vertical mixing and structure as well. Northward, freshwater transport as sea ice is pushed north by the wind. So imagine you're in the southern hemisphere, you're going towards the ocean. So this is Antarctic here. So ice shelf, as we said, fresh water forms, water from the melting ice shelves because of the warm ocean can begin to affect the vertical structure. Salt input into the ocean during ice growth, driving mixing and entrainment of heat from deep water. So it's entrainment is basically when you have ability to lift the deeper water and mix them with the shallower water. So that requires energy. So you can get that energy from this convective mixing because of the brine rejection and driving mixing down. So you can see this arrow showing the mixing. Okay, so I'm not going to read the long caption, but let's leave this here. Basically, it's again about ice advance in the Arctic, ice retreat, and ice season duration. So trend of timing or duration in days per year. So many things are happening earlier. Ice retreat is happening earlier, which means summer sea ice can disappear, or at least September sea ice extent can decrease. And this is later or longer ice advance, which means freezing is happening later, and ice season duration is decreasing, so it's consistent with the loss of sea ice. Whereas in Antarctica, it's a very mixed picture. There are places where the everything is earlier, ice advance, ice retreat, and ice season duration are shorter in some places, longer in some places. So this is mixed response basically because the processes between the Arctic and the Antarctic are very different. The stratification, the wind changes. So natural variability is already different, and response of the natural variability to anthropogenic forcing is different, and then the feedbacks are also different. So ice albedo feedback, of course, remains the most important one. In the summer, enhanced sea ice loss is dominated by the ice albedo feedback. Snow-covered sea ice reflects more of the incident solar radiation, in case you didn't already know. As the ice melts, it reveals the dark ocean, which absorbs more solar radiation. The heat absorbed by the ocean melts more ice, which in turn promotes more solar heating of the ocean, thus creating a positive melting feedback. And this is kind of the main feedback in the ice age and deglaciation that had happened in the last couple of million years. You can think of the current period, the Holocene and the so-called Anthropocene, which is not an official geologic period, epoch, but uh, you can think of this as a warm period within an ice age because we still have glaciers over Antarctica, Greenland, mountains, and so on, right? When you have an ice age, the glacier extent is much, much more. Sea ice cover is much, much more. Global temperatures are much cooler. Precipitation is drier overall, dusty, and so on and so forth. So what is Arctic amplification? A robust feature of climate models that is consistent with observations is enhanced warming of the Arctic relative to lower latitudes. We already saw that in the trend plot. This warming is most often associated with the ice albedo feedback in autumn. As the ice cover retreats further in summer, this ice loss, CS loss, subsequent release of heat to the atmosphere from the ocean during the autumn freeze up and the resultant thinner ice cover through the winter and spring warms the atmosphere near the ice surface. Other important feedbacks that limit radiative cooling of the ice cover, such as increased humidity and cloud cover, and a warming of lower atmosphere also contribute to Arctic amplification. The term polar amplification has sometimes been used, but in both observations and modern climate models, there is little or no enhanced warming in the Southern Ocean, largely due to the effects of ocean circulation and limited summer ice cover. Okay, so just remember the contrast because the processes are complicated and the resultant temperature trends are very different. So you can see here Arctic amplification is very clear, polar amplification is very clear, whereas it's not at all clear over here because the ocean, the channel that runs around Antarctica complicates things and creates very different response in the natural variability to anthropogenic forcing. Okay, so you have to remember cold ocean and warm atmosphere and warm ocean and cold atmosphere and warm ocean and warmer atmosphere or less cold atmosphere all have different ways of exchanging heat. So if the Arctic atmosphere is warming because of warm, moist air intrusions that we talked about, then actually the loss from the ocean to the atmosphere, heat loss, can be reduced. Okay, so we'll come back and look at further details with trends, changes. There is a lot of good details on the uh, atmospheric and oceanic processes and feedbacks that obviously I'm being very brief about, but you should go back and read those. So I'm going to stop here. This will be about a 20-minute, 22-minute podcast, but that is okay, right?